Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete story behind one of the most tragic and important events in the history of space exploration, the Challenger Space Shuttle disaster. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, to focus, or to fall asleep while still learning about engineering and history. There will be no sudden sounds, no background music, and no emotional tone. Only the steady voice of information, carefully unfolding the events, the machines, and the decisions that led to the accident. Now, please sit back, close your eyes if you like, and let the story of the Challenger Space Shuttle begin. The Challenger Space Shuttle disaster is one of the most remembered and studied accidents in the history of modern engineering and space exploration, because it highlighted both the extraordinary achievements and the devastating risks of human spaceflight. On January 28, 1986, the Shuttle Challenger broke apart just 73 seconds after liftoff, killing all 7 crew members on board and sending shockwaves across the world. To understand the magnitude of this event, it is important to begin with the broader context of the shuttle program itself, the promises it carried, and the circumstances that led up to the launch. The Space Shuttle program was developed by NASA to provide a reusable spacecraft that could carry astronauts and cargo into orbit on a regular basis. Unlike earlier rockets, which were discarded after each launch, the shuttle was intended to be launched, landed, refurbished, and launched again. It was a symbol of technological progress and was seen as a bridge between experimental space exploration and a more routine form of space travel. Challenger was one of several shuttles in the fleet, and by the mid-1980s, it had already flown multiple missions successfully. For many people, the shuttle had become a familiar image of American space power, and the launches were televised as events of both scientific and national pride. However, as the shuttle program advanced, so did the pressure to meet schedules, to maintain public interest, and to prove that spaceflight could indeed be routine. The Challenger mission, designated STS-51L, was unique because it included Krista McAuliffe, a teacher selected to become the first civilian in space. Her presence was meant to inspire students and highlight the educational potential of space exploration, and it attracted enormous media attention. Millions of people, including many school children, were watching the launch live on television, something that gave the disaster its lasting emotional impact. The day of the launch was unusually cold for Florida, with temperatures far below what was typical for a shuttle mission. Icicles were visible on parts of the launch pad equipment, and engineers had raised concerns about the safety of the solid rocket boosters, which used rubber O-ring seals that might not function correctly in low temperatures. Despite these warnings, the launch was approved, and the shuttle lifted off from Kennedy Space Center at 11:38 a.m. local time. At first, everything appeared normal. But less than a minute into the flight, smoke began escaping from one of the joints in the right solid rocket booster, indicating a failure of the O-ring seal. The hot gases escaping from this joint weakened the external fuel tank, and within seconds the shuttle disintegrated in a fireball high above the Atlantic Ocean. The loss of Challenger was not only a technical failure, but also a human tragedy that exposed the limitations of decision-making within large organizations like NASA. In the immediate aftermath, all shuttle flights were suspended while investigations were carried out, and the Rogers Commission was appointed to find the causes. The introduction to this disaster must emphasize that the Challenger accident was not a sudden, unpredictable event, but the result of technical design flaws, environmental conditions, and organizational choices that combined to produce catastrophe. For students of engineering, The Challenger story serves as a case study in how technology, human judgment, and safety culture intersect. It is a reminder that even the most advanced machines can fail when small details are overlooked, and that pressure to succeed can sometimes override caution. The disaster reshaped NASA's approach to risk, accountability, and communication, and it remains a cornerstone example used in engineering education around the world. As we begin this journey into the details of the Challenger disaster, it is essential to keep in mind that this event was more than a single explosion. It was a turning point that influenced how engineers, scientists, and policymakers think about safety and responsibility in high-stakes projects. The story begins with the promise of the shuttle program, the confidence of a nation in its technological prowess, and the belief that spaceflight was becoming ordinary, only to be shattered by the reality of engineering limits and the consequences of ignoring warnings. This introduction frames the Challenger disaster not just as a historical accident, but as a lesson in the enduring balance between ambition and caution in engineering. The Space Shuttle program was created by NASA during the 1970s as a bold response to the need for a more sustainable and reusable method of spaceflight, and it represented a dramatic shift from the expendable rockets of the Apollo era. Whereas the Apollo missions were designed for one-time use and focused on reaching the moon, the shuttle was designed to be a versatile vehicle that could transport astronauts, satellites, and cargo into orbit while being able to return safely, land on a runway, and fly again after refurbishment. The promise of reusability was central to the shuttle's purpose, as NASA envisioned dozens of flights each year, reducing costs and making access to space more routine. The shuttle was also promoted as a workhorse for scientific experiments, satellite deployment, construction of space stations, and even potential defense applications during the Cold War. This broad range of tasks placed high expectations on the design, which needed to combine the features of a spacecraft, an aircraft, and a heavy-lift rocket. In theory, this flexibility made the shuttle revolutionary, but in practice, it introduced significant engineering compromises. The shuttle consisted of three main parts: the orbiter, which carried the crew and payload; the external fuel tank, which provided propellant for the main engines; and the two solid rocket boosters, which provided the thrust necessary to escape Earth's gravity. Unlike conventional rockets, the solid rocket boosters were designed to be recovered and reused, parachuting into the ocean after separation and being refurbished for future launches. The orbiter itself resembled a plane, with wings that allowed it to glide back to Earth and land on a runway, making it appear familiar yet futuristic. NASA presented the shuttle as a system that could make spaceflight as regular as commercial aviation, but this was always more aspirational than realistic. The shuttle program was also tied to political expectations, as NASA needed continued funding after Apollo. Selling the shuttle as a cost-effective, reusable, and multi-purpose system helped secure support from Congress and the White House, and it was portrayed as essential to maintaining American leadership in space during an era of geopolitical competition with the Soviet Union. The shuttle was more than a machine. It was a symbol of national pride and technological dominance, and this symbolism placed pressure on NASA to perform reliably, frequently, and visibly. By the early 1980s, shuttles like Columbia, Challenger, Discovery, and Atlantis were launched on a regular basis. Each mission broadcast to millions of viewers and celebrated as demonstrations of progress. The program was ambitious in scope, with plans for nearly routine flights that would service satellites, deploy probes, and eventually help build an orbital station. Challenger itself had already completed several missions successfully before 1986, which gave many within NASA and the public the impression that shuttle launches were becoming normal and almost safe. The reality, however, was that each launch remained inherently dangerous, involving complex engineering systems exposed to immense forces and extreme temperatures. Yet the push to achieve high flight rates meant that safety margins were often stretched, and concerns raised by engineers were sometimes balanced against the political and financial desire to keep the program moving forward. The ambitions of the shuttle program were not just technical, but also educational and inspirational, which is why the Teacher in Space project was conceived. By placing a civilian teacher, Krista McAuliffe, on board Challenger, NASA sought to inspire an entire generation of students to look toward the stars and see space not only as a scientific frontier, but also as a place for ordinary citizens. This ambition raised public interest and media attention, ensuring that the Challenger launch would be watched live by countless people across the United States, particularly school children. The vision of the shuttle was that of routine exploration, cost savings, scientific breakthroughs, and national pride. But the technical complexity and organizational challenges of the program meant that reality often fell short of expectations. As we reflect on the ambitions of the shuttle program, it is clear that its goals of reusability and regular access to orbit were visionary, but were not fully supported by the engineering and management practices of the time. The Challenger disaster would later reveal the dangerous gap between what was promised and what was achievable, showing that ambition without adequate caution can have devastating consequences. The program's goals were noble, and its achievements were remarkable, but the balance between political pressure, public image, and technical safety was never easy to maintain. It is within this ambitious context that the story of Challenger must be understood, for the disaster was not just an accident of engineering, but a collision between aspiration and reality. The design and engineering of the Challenger shuttle reflected both the strengths and the compromises of the entire shuttle program, because it was created to be a multi-purpose vehicle that could satisfy a wide range of demands. Challenger, officially known as Orbiter Vehicle 099, was initially constructed as a test article for ground vibration testing before being modified for spaceflight due to the need for an additional orbiter in the fleet. Its structure and systems were similar to those of Columbia, the first operational shuttle, but Challenger benefited from design improvements that made it lighter and somewhat more efficient. The shuttle itself was a complex assembly of millions of parts, integrating technologies from aerospace, materials science, and computing. The orbiter was the central component, housing the crew cabin, payload bay, and the three main engines mounted at the rear. The orbiter measured roughly 37 meters in length, with a wingspan of about 24 meters, giving it the appearance of a futuristic airplane. Its payload bay was large enough to carry satellites, laboratory modules, or components for space stations, while the crew cabin could support up to 7 astronauts. Attached to the orbiter was the massive external fuel tank, which supplied liquid hydrogen and liquid oxygen to the main engines during liftoff. This tank was the largest single piece of the shuttle system and was discarded after each launch, burning up in the atmosphere after separation. On either side of the external tank were the 2 solid rocket boosters, which provided the majority of thrust during the first 2 minutes of flight. Each booster was more than 40 meters tall and contained segmented sections filled with solid propellant. The boosters were designed to be recovered from the ocean, refurbished, and reused for later missions. While this design contributed to the reusability concept of the shuttle, it also introduced the critical weakness that would ultimately cause the Challenger disaster. The O-ring seals in the joints between the booster segments were vulnerable to changes in temperature and pressure, and these seals were never intended to operate reliably in the unusually cold conditions present on the morning of January 28, 1986. The engineering complexity of Challenger was immense, with thousands of subsystems that needed to work together under extreme conditions. The thermal protection system, made of ceramic tiles, shielded the orbiter from the intense heat of re-entry, while the hydraulic systems controlled the movement of the wings, rudder, and landing gear. The shuttle's avionics combined digital and analog components, reflecting the technological transition of the era, and the flight control system relied on multiple redundant computers to ensure reliability. Every part of the shuttle was designed to push the boundaries of aerospace engineering. But with this ambition came risks. Weight constraints meant that materials were sometimes pushed to their limits, and the demand for reusability introduced design choices that favored refurbishing over replacement. Challenger's design represented a balance between what was technologically possible, politically required, and financially constrained. It was a vehicle expected to launch satellites for commercial clients, conduct scientific experiments for universities, support military missions, and inspire the public with visible demonstrations of progress. This broad mission profile forced engineers to make compromises that affected safety margins. For example, the segmented design of the solid rocket boosters was chosen for manufacturing and transport reasons, but it introduced more points of potential failure than a single-piece booster would have. Similarly, the thermal protection tiles were lightweight and reusable, but fragile and prone to damage during launch and landing. Challenger's design therefore embodied both innovation and vulnerability. Engineers knew that certain risks existed, but the drive to maintain schedules and demonstrate routine access to space often overshadowed those concerns. When examining Challenger's engineering, one must remember that no system as complex as the shuttle could ever be entirely without flaws. Yet the expectation was that these flaws could be managed, that the redundancies and procedures would prevent catastrophe. Challenger flew successfully 9 times before its final mission, proving that the design could perform as intended under normal conditions. However, the flaws that seemed manageable during earlier flights became critical under the unique circumstances of that cold January morning. In understanding Challenger's design and engineering, it becomes clear that the shuttle was both a triumph of ingenuity and a system constrained by compromise. It pushed the limits of technology and demonstrated that reusable spacecraft were possible, but it also showed how small weaknesses, when combined with organizational pressures, could lead to failure. The design of Challenger set the stage for the events of 1986, and it remains an example of both the brilliance and the fragility of engineering at the edge of possibility. The preparations for the Challenger mission, STS-51L, showed the immense complexity of getting a shuttle ready for launch and the many layers of work required before a flight could begin. Challenger was scheduled to lift off from Launch Complex 39B at Kennedy Space Center in Florida, a launch site originally built for the Apollo program and later adapted for the shuttle. The orbiter was rolled out on a crawler transporter and raised on the mobile launch platform, standing with the external tank and solid rocket boosters attached. Technicians checked every system, from communications to fuel lines, ensuring that the orbiter, tank, and boosters were properly connected and ready. The mission itself had several objectives, including deploying a satellite, releasing a spacecraft to study Halley's Comet, and most notably featuring Krista McAuliffe, a teacher who had been chosen to represent the Teacher in Space project. Her presence made this mission one of the most publicized in shuttle history, as schools across the United States planned to watch her lessons from orbit. The launch was originally scheduled for January 22, 1986, but delays soon pushed it back. Technical issues, such as problems with a hatch handle, bad weather at a transatlantic landing site, and conflicts with earlier missions, all contributed to the schedule slipping day by day. These delays created mounting pressure within NASA to proceed with the launch and prove that the shuttle could keep up with its promise of frequent and reliable flights. By January 27th, the shuttle was on the pad, fueled and ready. But a new concern appeared. The forecast predicted very cold temperatures for the night and following morning, far below what was usual for a Florida launch. Morton Thiokol engineers, who built the solid rocket boosters, warned that the rubber O-ring seals in the joints might not function correctly in such cold conditions. Teleconferences were held between NASA officials and the company, with engineers arguing strongly for delay. However, under pressure to meet the schedule, managers eventually approved the launch, overruling the warnings. Overnight, the temperatures dropped below freezing, and ice built up around the launch pad structures. Photographs taken early on January 28th showed long icicles hanging near the shuttle, and technicians worked to remove as much ice as possible before fueling operations began. Despite the strange appearance of the launch pad, the decision stood. Challenger would launch that morning. The crew arrived and entered the orbiter, going through standard pre-flight checklists. Francis Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, and Krista McAuliffe settled into their seats, connected their communications, and waited as the countdown continued. Ground crews loaded the massive external tank with liquid hydrogen and liquid oxygen, and Mission Control in Houston monitored each system. The countdown sequence included planned holds for verification, but each system was cleared for flight. To the outside world, the sight of Challenger on the pad was awe-inspiring. The shuttle stood tall against the clear blue sky, but its orange fuel tank and white boosters were ringed by frost and traces of ice. Millions of people were ready to watch the launch live, with television cameras broadcasting across the country. For NASA, this was to be another demonstration of progress, another step toward routine space travel, and another chance to inspire the public. Yet the technical concerns about the O-rings remained unresolved, and the cold air of that January morning made the risks greater than ever. The launch pad preparations, while thorough in appearance, masked the deeper tensions between safety and schedule. The stage was set, the systems were ready within official limits, the astronauts were waiting, and the countdown reached towards zero. What appeared to be another triumph of technology was in fact the beginning of one of the greatest tragedies in the history of spaceflight. The crew of Challenger's final mission, STS-51L, represented a diverse group of astronauts and specialists who embodied the spirit of exploration, science, and education that the shuttle program sought to promote. Francis R. Scobie served as the mission commander, a skilled pilot and veteran of previous spaceflight, responsible for overall leadership and the safe execution of the mission. Beside him in the cockpit sat Michael J. Smith, the pilot of the shuttle, a former Navy aviator making his first trip to space, tasked with assisting in navigation, systems management, and supporting Scobie during launch, orbit, and re-entry. The mission specialists included Judith A. Resnick, an electrical engineer and the second American woman in space, who had already flown on a previous shuttle mission and was assigned to operate the shuttle's robotic arm and conduct experiments. Ellison S. Onizuka, the first Asian American in space, was a mission specialist trained in systems engineering and responsible for technical experiments and operational support. Ronald E. McNair, a physicist and accomplished saxophonist, was another mission specialist, carrying out scientific payload operations and experiments during the planned orbital phase. Gregory Jarvis, a payload specialist employed by Hughes Aircraft, was on board to conduct research on fluid dynamics in microgravity, part of a commercial payload contract. Finally, Krista McAuliffe, a social studies teacher from New Hampshire, was selected as the first participant in NASA's Teacher in Space project, a program designed to demonstrate that ordinary civilians could participate in space missions and to inspire millions of students. She planned to conduct 2 live lessons from orbit, broadcast to classrooms across the country, focusing on the excitement of science, technology, and human exploration. The composition of the crew reflected NASA's broader goals of combining technical expertise with public outreach, proving that the shuttle was not only a platform for experiments, but also a tool for education and inspiration. The mission goals were ambitious yet symbolic. The deployment of the Tracking and Data Relay Satellite B was critical to NASA's communications infrastructure, improving contact with spacecraft and extending the reach of ground-based tracking systems. The release of the Spartan Halley spacecraft was timed with the appearance of Halley's Comet, one of the most studied celestial objects, offering a chance to gather valuable scientific data during its once-in-a-lifetime approach. Gregory Jarvis's experiments on fluid behavior in weightlessness were aimed at advancing technology for satellites and space stations. McAuliffe's role, however, was designed to capture the imagination of the public. Through her classroom lessons, she would show students that space was not only for scientists or military pilots, but also a place for teachers and ordinary citizens, a message intended to broaden interest in science and strengthen support for NASA. The inclusion of McAuliffe made STS-51L one of the most publicized missions in shuttle history. Media coverage was extensive, and schools across the nation prepared to tune in to her lessons. For NASA, this was a chance to reinforce the idea that the shuttle was ushering in a new era of routine, accessible spaceflight, a vehicle that could carry not only astronauts, but also representatives of the public. The crew trained extensively together, forming strong bonds during the months leading up to launch. They rehearsed procedures, practiced emergency scenarios, and familiarized themselves with the shuttle's systems. Each member had a specific role, but they were also trained to work as a cohesive team, prepared to adapt to the unexpected challenges of spaceflight. Their presence on Challenger symbolized both the technical aspirations of the shuttle program and the human side of exploration. The crew embodied professionalism, curiosity, and optimism, qualities that made them ideal representatives of NASA's goals. As the countdown to launch neared completion, they carried with them not only the hopes of the agency, but also the attention of a global audience. Millions would watch as the crew prepared to embark on their mission, unaware that tragedy awaited. The Challenger crew's mission goals combined scientific progress, commercial experimentation, and educational outreach, making STS-51L a unique and historic flight in the shuttle program. It was designed to showcase the shuttle's versatility and potential, to inspire students, to serve government and commercial needs, and to advance scientific understanding. This blending of technical and symbolic purposes placed the crew in a spotlight, unlike any previous mission. Their story remains central to understanding the Challenger disaster, because it highlights what was at stake. Not only satellites and experiments, but also the lives of 7 people who represented the promise of space exploration. The crew of Challenger stood as a reminder of the human courage and ambition behind every engineering achievement and their mission goals were both a reflection of NASA's vision and a testament to the risks inherent in pursuing it. The morning of January 28th, 1986, was unlike any other in the history of shuttle launches because of the unusually cold weather that gripped Florida and created conditions that were far outside the normal operating range for the Space Shuttle Challenger. Overnight, the temperature had dropped below freezing, and this was highly unusual for the subtropical climate of Cape Canaveral. When technicians and engineers arrived at the launch pad early in the morning, they were met with the sight of icicles hanging from the steel structures, frost-coating handrails, and patches of ice clinging to the shuttle's massive external fuel tank. The visual appearance of the launch pad was startling, and photographs taken at dawn captured images that later became iconic, showing the shuttle standing tall but surrounded by ice, a symbol of the risky conditions in which the launch was to proceed. Engineers had already warned about the vulnerability of the solid rocket booster O-ring seals to cold temperatures, and these warnings were particularly urgent because the forecast predicted lows around 22 degrees Fahrenheit, far colder than any previous shuttle launch. The O-rings were made of rubber, a material that loses flexibility when chilled, and this stiffness could prevent the rings from sealing properly against the immense pressure of ignition. The night before the launch, a heated teleconference had been held between NASA and Morton Thiokol, the contractor responsible for the boosters, in which several engineers argued strongly against proceeding. They presented data showing how O-ring erosion was more likely at low temperatures, but their concerns were overridden by management after pressure from NASA to keep the launch on schedule. This decision became one of the most consequential in aerospace history. On the morning of the launch, ground crews attempted to assess and mitigate the risks posed by the ice. They conducted inspections and used cameras to evaluate the buildup on the shuttle and the surrounding structures. Some of the ice was removed, but much of it remained, as the low temperatures persisted even after sunrise. Despite these observations, NASA management concluded that the situation was acceptable and continued with the countdown. For the astronauts, the cold morning was noted but did not alter their routine. The crew, dressed in their bright orange launch suits, boarded a transport van and traveled to the launch pad, where they ascended the tower and entered the orbiter. Inside the cabin, they strapped into their seats, checked their instruments, and established communication with mission control. While they were shielded from the cold by the shuttle's structure and heating systems, they were still aware that the launch conditions were unusual. Outside, the spectacle of the shuttle on the pad captivated the public. Media crews filmed the gleaming white orbiter against the clear blue sky, while the orange external tank stood out even more brightly with streaks of frost along its surface. Millions of viewers, including countless schoolchildren waiting to see Krista McAuliffe's historic journey, were preparing to watch the launch live. The cold weather gave the scene a unique clarity, with the shuttle appearing almost surreal against the crisp morning air. Yet beneath the striking visuals was a technical reality that made this one of the most dangerous launches ever attempted. As the final hours of preparation passed, the fueling of the external tank was completed with liquid hydrogen and liquid oxygen, supercooled propellants that only added to the icy appearance of the shuttle. The countdown proceeded through its scheduled holds, and despite concerns expressed in earlier meetings, no official stop was called. The determination to launch reflected not only technical optimism, but also organizational momentum, the feeling that the mission had already been delayed long enough and must now go forward. When the final go for launch was given, Challenger stood poised to lift off in temperatures that were well below the levels ever tested for the booster joints. This cold morning represented the convergence of natural forces, human ambition, and overlooked warnings, a combination that set the stage for disaster. The Challenger disaster cannot be understood without grasping the significance of the freezing weather and the way it influenced both the technical performance of the shuttle and the decision-making process of those in charge. The cold air of January 28, 1986, was not just a background detail, but a central factor in the tragedy that followed. The solid rocket boosters used on the Space Shuttle Challenger were among the most powerful rocket engines ever built, each providing millions of pounds of thrust to lift the shuttle off the launch pad and propel it through the lower atmosphere. These boosters stood more than 40 meters tall and were divided into cylindrical segments that were manufactured separately and then transported to the Kennedy Space Center, where they were assembled. Each segment contained solid propellant, a mixture designed to burn with incredible energy and consistency. When ignited, the boosters produced an immense force that, combined with the shuttle's three main engines, lifted the entire vehicle skyward. Unlike liquid-fueled rockets, which can be throttled or shut down, solid rocket boosters cannot be stopped once they are lit, which made their design and reliability critical to crew safety. To connect the booster segments, engineers used joints sealed with large rubber O-rings designed to prevent the hot combustion gases from escaping during ignition and flight. The O-rings were positioned in grooves within the joints, and when the booster pressurized, the rubber was supposed to expand and seal tightly, preventing leaks. In theory, this was a simple and effective solution, but in practice, the O-rings had limitations that became increasingly apparent as the shuttle program advanced. During earlier missions, evidence of erosion and partial burns on the O-rings had been discovered after recovery of the boosters, suggesting that hot gases had penetrated areas they were not meant to reach. Engineers at Morton Thiokol, the company responsible for manufacturing the boosters, raised concerns about these findings, warning that under certain conditions, the O-rings might fail entirely. One of the most significant factors affecting the O-rings was temperature. At warmer temperatures, the rubber was flexible and able to respond quickly to pressure changes, creating a good seal. At colder temperatures, however, the material became stiff and less able to move into place in time to prevent hot gas leaks. This delay in sealing created what engineers called blow-by, where gases escaped past the first O-ring and reached the second, or in worse cases, burned through the joint itself. In the years leading up to Challenger, there were repeated warnings from engineers that launches in cold weather posed unacceptable risks. Yet these concerns were often minimized or deferred because the shuttle program was under pressure to maintain its ambitious schedule. The design of the booster joints also contributed to the risk. The joints were not perfectly rigid, and during ignition, they tended to flex, a phenomenon known as joint rotation. This flexing widened the gap the O-rings were meant to seal, forcing the rubber to work even harder to maintain integrity. The combination of joint rotation and stiff O-rings in cold conditions created a dangerous scenario, one that was understood by some engineers but not adequately addressed by management. The morning of January 28, 1986, brought temperatures so low that the O-rings were well outside their tested range. Morton Thiokol engineers strongly advised against launch, citing the inability of the O-rings to perform as designed in such cold. They presented data showing erosion in earlier flights and predicted that the risk was far higher under those conditions. However, after internal debate and pressure from NASA, Morton Thiokol management reversed its recommendation and approved the launch, a decision that would later be identified as a critical organizational failure. The O-rings, though small compared to the size of the booster, became the weak link in the entire shuttle system. Their role was absolutely vital because a breach in the booster joint would allow flame and pressure to escape and strike nearby structures, including the massive external tank filled with liquid hydrogen and liquid oxygen. The Challenger disaster demonstrated that even the most powerful and complex machines can be brought down by a component that seems minor, but is in fact essential. The solid rocket boosters were engineering marvels, yet their segmented design introduced vulnerabilities that were never fully resolved. The O-ring seals, simple in appearance but complex in function, represented the fine line between success and failure in high-risk engineering. The story of the Challenger cannot be told without focusing on these seals, for they were the precise point of failure that transformed a launch into a tragedy. This section highlights how the boosters, designed for strength and reusability, carried within them a flaw that was known but underestimated, a flaw that revealed itself catastrophically on that cold January morning. The Challenger disaster cannot be understood without examining the early warnings and concerns raised by engineers in the years before the launch of STS-51L, because these warnings revealed the vulnerabilities of the shuttle's design and the organizational culture that failed to address them. From the earliest shuttle flights, evidence began to appear that the O-ring seals in the solid rocket booster joints were not performing as expected. After the very first shuttle mission, STS-1 in 1981, recovered booster hardware showed signs of erosion and soot, an indication that hot gases had partially burned past the primary O-ring. This was not what the design intended, and although the secondary O-ring prevented a complete failure, the erosion was an unmistakable sign of weakness. Over subsequent missions, similar signs were found again and again, confirming that the problem was not an isolated anomaly, but a recurring risk. Engineers at Morton Thiokol, the contractor that built the boosters, took these signs seriously. They documented blow-by, erosion, and charring on O-rings, and repeatedly warned that under the right conditions, a catastrophic failure could occur. Reports were written, data were collected, and concerns were voiced during technical meetings. One of the engineers who became closely associated with these warnings was Roger Boisjoli, who argued that the O-rings could not be relied upon in cold temperatures, and that the shuttle should not be launched outside their tested range. He and others within Morton Thiokol explained that the rubber material of the O-rings lost flexibility as temperatures dropped, delaying the sealing action needed to contain the hot gases during booster ignition. At normal or warm conditions, this delay might be manageable, but at low temperatures, the O-rings could be too stiff to respond in time, allowing flame to escape through the joint. The evidence was accumulating, but the response from NASA management was often dismissive. Each time erosion occurred without causing total failure, it was classified as an acceptable risk, a phenomenon known as normalization of deviance. Because the system had survived erosion before, managers grew accustomed to the idea that the O-rings could continue to perform adequately, even though engineers insisted the margin of safety was far thinner than it appeared. By 1985, these concerns had reached a critical point. Several missions showed increasing signs of O-ring damage, and Morton Thiokol engineers urged NASA to reconsider the launch criteria. Yet the shuttle program was under immense political and financial pressure to maintain a high flight rate, with goals of up to 24 launches a year. Delays were costly, not only in dollars, but also in reputation, as the shuttle had been promoted as a routine space vehicle. In this environment, safety concerns competed with schedule demands, and warnings from engineers were sometimes interpreted as obstacles to progress, rather than urgent alerts. Meetings were held, where data on O-ring erosion were presented, but management often pushed for reassurances, rather than accepting the full implications of the evidence. This tension became most visible in the hours leading up to Challenger's launch. On the night of January 27, 1986, Morton Thiokol engineers strongly recommended against launching in the freezing temperatures predicted for the next morning. They presented charts and calculations showing that the O-rings could not be expected to seal at such low temperatures. During the teleconference, engineers argued passionately that the risks were too great. But managers, under pressure from NASA, eventually overruled them. The recommendation was changed to approve the launch, a decision that shocked those who had been warning of disaster for years. These early warnings, if taken seriously, could have prevented the tragedy. The evidence of O-ring erosion was clear. The data on temperature sensitivity were known, and the engineers' voices were loud. But the organizational culture of NASA and its contractors prioritized meeting deadlines and maintaining public confidence. The Challenger disaster thus became not only a technical failure, but also a human and managerial one, in which warnings were disregarded until it was too late. The story of these early concerns demonstrates how complex systems fail, not just because of faulty parts, but because of faulty decisions. It shows how organizations can become blind to risk when success breeds complacency, and how engineers who see danger can struggle to make their voices heard in the face of institutional momentum. Challenger's fate was sealed long before the countdown began, and the warnings from engineers remain one of the most tragic aspects of the disaster, a reminder that knowledge without action is powerless. The launch of the Space Shuttle Challenger on the morning of January 28, 1986, followed the same basic sequence that had been rehearsed and carried out on previous missions. And in the opening moments, everything appeared to proceed normally, giving no immediate indication of the disaster that was about to unfold. At 11:38 a.m. Eastern Standard Time, after the countdown reached zero, the three main engines of the orbiter ignited first, drawing fuel from the massive external tank filled with liquid hydrogen and liquid oxygen. The engines roared to life, gimbaling to maintain balance and building up thrust, while computers confirmed their performance. A few seconds later, the two solid rocket boosters ignited, producing a combined thrust of more than 6 million pounds, instantly lifting the shuttle stack from the pad in a bright flash of flame and smoke. The hold-down bolts that had secured the shuttle released, and Challenger began its ascent into the clear blue Florida sky. As the shuttle rose, the familiar twin plumes of white smoke trailed behind the boosters, and the sound of the launch reverberated across the coastline, thrilling the thousands of spectators who had gathered to watch in person, and the millions more who tuned in on live television broadcasts. For the crew inside the orbiter, the launch was a controlled chaos of noise, vibration, and acceleration. Yet all indications from their instruments and communications with mission control suggested that systems were functioning within expected parameters. In reality, however, trouble had already begun. Almost immediately after liftoff, cameras captured a puff of dark smoke near one of the joints on the right solid rocket booster, a sign that the primary O-ring seal had failed to contain the hot gases. In the frigid conditions of that morning, the rubber O-rings had stiffened and were unable to expand quickly enough to seal the joint, allowing combustion gases to escape. For a brief period, residue from the burning fuel temporarily sealed the gap, preventing a catastrophic leak in the first seconds of flight. This phenomenon created a false sense of security, because from the perspective of mission control and the crew, the launch seemed normal. The shuttle accelerated rapidly, passing through the region known as Max Q, the point of maximum aerodynamic pressure, where structural stress on the vehicle was greatest. Challenger performed as expected, climbing higher and faster, with the boosters continuing to deliver immense thrust. At this stage, the astronauts would have been monitoring their instruments, following procedures, and feeling the tremendous force of acceleration pushing them back into their seats. Meanwhile, ground controllers observed telemetry data that showed no critical alarms, reinforcing the impression that everything was proceeding according to plan. The shuttle passed through 15, 30, and then 40 seconds of flight, with the plume of exhaust trailing dramatically against the clear sky. Spectators on the ground cheered as Challenger appeared to climb steadily, and for many schoolchildren watching across the country, the moment was one of awe and inspiration, especially because they were waiting to see teacher Krista McAuliffe make history. Yet the hidden damage to the booster joint continued to worsen, and the temporary seal of soot and debris could not withstand the increasing pressure as the shuttle climbed higher. Hot gases gradually eroded the field joint, weakening the structure of the booster and allowing flames to leak outward. The crew, mission control, and the public remained unaware of these developments, as the external signs of trouble were subtle and not yet visible in dramatic form. The shuttle continued to gain altitude, passing through 50 and 60 seconds of flight, moving faster than the speed of sound, and leaving behind a cone of vapor known as a shock collar. The first minute of the launch was always considered one of the most dangerous phases, but Challenger seemed to have cleared the initial hurdles successfully. The bright Florida morning provided clear views for cameras that tracked the ascent, and the footage showed a spacecraft appearing strong and steady. At 70 seconds, Challenger was more than 40,000 feet above the Atlantic, traveling at nearly Mach 2, and both the crew and controllers anticipated the upcoming milestone of booster separation. The launch sequence, in its first moments, appeared routine, but beneath the surface, the critical flaw in the booster joint was progressing toward disaster. The Challenger flight demonstrated how catastrophic failure can develop silently, hidden within a system that otherwise seems to be functioning properly. The opening 73 seconds of flight are remembered today as a mixture of triumph and tragedy, because in that brief time, Challenger achieved liftoff, overcame the initial stresses of launch, and climbed toward orbit, only to be destroyed moments later. The defining moment of the Challenger disaster was the critical failure of the right solid rocket booster joint, where the O-ring seals eroded under the extreme pressure and temperature of ignition and ascent, eventually allowing a jet of flame to escape and destroy the shuttle. The failure was the result of a chain of factors that began even before liftoff, when the unusually cold temperatures stiffened the rubber material of the O-rings and prevented them from expanding quickly enough to seal the joint properly. At the moment of booster ignition, hot gases under enormous pressure forced their way into the gap, burning past the primary O-ring. For a short time, residue from the combustion sealed the joint temporarily, creating what engineers later called a blow-by condition, in which gases passed through but did not yet burn a full hole. This temporary seal held during the first seconds of flight, which is why the shuttle appeared to launch normally. However, as Challenger climbed and aerodynamic forces increased, the weakened joint began to open further due to joint rotation, a flexing of the booster casing that widened the gap between segments. The cold, stiff secondary O-ring was unable to move into place quickly enough to serve as a backup. By the time Challenger reached about 40 seconds into the flight, television cameras captured unusual plumes of smoke around the right booster, signs that the erosion was progressing. At around 58 seconds, the flame jet became visible as it broke through the joint, producing a bright glow against the side of the booster. The escaping jet of flame was aimed directly at the external fuel tank, which contained hundreds of thousands of gallons of liquid hydrogen and liquid oxygen, the volatile propellants for the orbiter's main engines. As the flame cut into the lower part of the external tank, it began to weaken the structural strut, connecting the booster to the tank. The hydrogen tank itself was breached, allowing pressurized hydrogen to escape, and telemetry data later showed a drop in pressure in the external tank systems. At the same time, the shuttle was experiencing maximum aerodynamic loads, adding stress to the already compromised structure. At 73 seconds into the flight, the combined effects of the flame jet, the weakened strut, and the breached hydrogen tank caused the external tank to collapse. A massive structural failure followed, tearing apart the orbiter and boosters in an instant. From the ground, spectators saw what looked like a huge fireball in the sky, with white trails of smoke and debris spiraling outward. The orbiter Challenger was not destroyed by an explosion in the conventional sense, but by the rapid breakup of the external tank and the violent forces that tore the shuttle apart. The crew cabin separated from the rest of the orbiter, but was unable to withstand the aerodynamic forces, and it ultimately broke apart as it fell into the ocean. For mission control and the astronauts, there was little warning of the final catastrophic moment. The last words from pilot Michael Smith were a calm acknowledgement of an instrument reading just before the shuttle disintegrated. The failure happened so quickly that there was no time for the crew to react or attempt any escape, and no escape system existed for a shuttle at that altitude and velocity. The O-ring erosion and seal breach represented not only a technical breakdown, but also a symbolic one, because it was a problem that had been identified years earlier, but never properly resolved. Engineers had repeatedly documented erosion and warned that the seals were vulnerable to temperature, yet the issue was normalized as an acceptable risk. On that cold January morning, the combination of environmental conditions, flawed design, and managerial pressure to launch created the perfect setting for disaster. The breach of a single seal in a booster joint cascaded into the loss of the entire shuttle, showing how even the smallest component can determine the fate of the largest and most advanced machine. The Challenger tragedy is therefore remembered as an event where the critical failure of an O-ring not only destroyed a spacecraft, but also revealed the consequences of ignoring warnings, pushing schedules, and underestimating risk. This failure became the focal point of subsequent investigations, and it stands today as one of the most studied and discussed technical breakdowns in engineering history. At 73 seconds after liftoff, the Space Shuttle Challenger experienced the catastrophic structural breakup that ended the mission and claimed the lives of its 7 crew members, a moment that remains one of the most haunting images in the history of space exploration. To spectators on the ground, and millions watching live television broadcasts, the shuttle appeared to suddenly explode in a bright flash against the clear blue sky, sending trails of smoke and debris outward in chaotic patterns. In reality, the shuttle did not explode in the traditional sense, but rather disintegrated as the external fuel tank ruptured under the combined stresses of aerodynamic forces and the flame jet from the failed booster joint. The release of liquid hydrogen and liquid oxygen created a massive fireball that gave the impression of an explosion, but the orbiter itself was torn apart by structural failure rather than destroyed by combustion. High-speed cameras later revealed the sequence of events in chilling detail. As the flame from the right solid rocket booster burned through the strut connecting it to the external tank, the booster pivoted outward, further destabilizing the stack. The escaping flame simultaneously breached the hydrogen tank, releasing enormous quantities of propellant that ignited and engulfed the shuttle. At that moment, the forces acting on the orbiter exceeded its structural limits, ripping it into multiple sections. The wings, tail, and payload bay separated violently, while the crew cabin detached largely intact before being overwhelmed by aerodynamic stress as it tumbled through the atmosphere. For Mission Control in Houston, the first indication of disaster came when telemetry data abruptly ceased, followed by the sight of the fireball on live camera feeds. The flight director and controllers struggled to process what had happened, initially describing it as a major malfunction, before it became clear that the shuttle had been destroyed. For the families of the crew watching from the viewing stands, the sight of the sudden fireball was devastating, an incomprehensible transformation of triumph into tragedy within seconds. In the moments after the breakup, the solid rocket boosters continued to fly uncontrollably, their thrust still active because solid fuel cannot be shut off. The boosters veered wildly across the sky, creating further plumes of smoke until range safety officers sent destruct commands to ensure they did not threaten populated areas. Meanwhile, debris from the shuttle rained down into the Atlantic Ocean, scattering across a wide area and marking the beginning of a long and painful recovery operation. The breakup was not instantaneous for the crew compartment, which remained structurally intact for a short period after separation. Investigations later concluded that the crew likely survived the initial disintegration of the orbiter, though they would have been subjected to extreme forces and a rapid loss of cabin pressure. Without an escape system or a method of surviving the aerodynamic loads at such altitude and velocity, the crew cabin eventually broke apart as it descended, striking the ocean at a speed that was not survivable. The haunting reality that the crew may have been conscious for some portion of the descent added to the tragedy of the disaster. The breakup of Challenger in the sky was more than a technical failure. It was a deeply symbolic moment that shattered public confidence in the shuttle program. The dramatic images of smoke trails, twisting plumes, and falling debris became etched in the collective memory of a generation, a stark reminder of the risks of spaceflight and the consequences of ignoring warnings. What had begun as a mission of inspiration, highlighted by the presence of a teacher meant to bring the excitement of space to classrooms, ended in horror before the eyes of those very students. The 73 seconds between liftoff and breakup encapsulated the fragile line between success and catastrophe in engineering. The Challenger's destruction revealed how a single point of failure in the solid rocket boosters cascaded into the loss of an entire vehicle and crew, an outcome that had been predicted but not prevented. The breakup in the sky remains the defining image of the disaster, one that continues to be studied, remembered, and mourned as one of the darkest moments in the history of space exploration. In the immediate aftermath of the Challenger disaster, attention shifted from the shock of the breakup in the sky to the urgent and massive search and recovery operations that followed. Operations that would take weeks and involve thousands of personnel working across air, sea, and land. When Challenger disintegrated 73 seconds into flight, the debris from the orbiter, the external tank, and the solid rocket boosters fell into the Atlantic Ocean, scattering across a wide area approximately 18 miles off the coast of Florida. The US Coast Guard was the first to respond, dispatching ships and helicopters to the debris field to secure the area and begin the grim process of recovery. They were soon joined by Navy vessels, NASA support ships, and civilian contractors, creating a coordinated fleet tasked with locating, retrieving, and cataloguing the remains of the shuttle. The debris field extended over hundreds of square miles, and the effort was complicated by rough seas, strong currents, and the sheer number of fragments that had to be recovered. Some pieces floated, including insulation and lighter materials, but the majority of the wreckage sank to the ocean floor, requiring divers, submersibles, and sonar equipment to locate. Navy divers played a crucial role, descending into difficult and dangerous underwater conditions to identify and raise pieces of the shuttle. The scale of the task was immense, as the orbiter had disintegrated into thousands of fragments, ranging from small shards of tile to large sections of wing or fuselage. Each recovered piece was carefully logged and transported to a hangar at the Kennedy Space Center, where engineers and investigators began the painstaking work of reconstruction. The goal was to piece together enough of the shuttle to understand the sequence of failure and confirm the cause of the disaster. Among the most sensitive aspects of the recovery was the search for the crew cabin and the remains of the astronauts. For weeks, nothing was found. But in March 1986, divers located a large section of the crew compartment on the ocean floor. The recovery of this section was conducted with great care and solemnity, and the remains of the 7 crew members were eventually recovered and returned to their families for burial. This part of the operation underscored the human cost of the tragedy and brought a deeply emotional dimension to what was otherwise a technical and logistical effort. The recovery also extended to the solid rocket boosters, which had continued to fly uncontrollably after the shuttle's breakup before being destroyed by range safety charges. Large portions of the boosters were retrieved from the ocean and examined closely, providing crucial evidence about the failure of the O-ring seals and the joint that had allowed flame to escape. These pieces became central to the investigation that followed, as they provided physical proof of the erosion and blow-by that engineers had feared. The recovery operations lasted for months, continuing into the spring and summer of 1986, with teams working tirelessly to bring up as much debris as possible. The process was not only technically challenging, but also emotionally heavy for those involved, as every piece of wreckage represented a fragment of a once proud and powerful machine that had been lost in a matter of seconds. The hangar at Kennedy Space Center gradually filled with rows of shuttle fragments laid out in grids, a somber mosaic that told the story of failure. For NASA, the recovery operations were essential to the investigation, but they also served as a stark reminder of the risks inherent in the shuttle program. The visual of the broken orbiter, laid out piece by piece, conveyed the scale of destruction and the fragility of human engineering against the unforgiving realities of physics and spaceflight. The Challenger recovery was one of the largest peacetime search and salvage operations in American history, involving countless hours of effort and the dedication of military, civilian, and NASA personnel working together under extraordinary circumstances. The search and recovery operations after the disaster thus stand as both a technical achievement and a solemn act of respect. They provided the evidence needed to understand why Challenger was lost. They returned the crew to their families, and they allowed the nation to begin the long process of mourning and reflection. The recovery was not the end of the Challenger story, but the bridge to the investigations and reforms that would follow, ensuring that the lessons of the tragedy would be documented and remembered. In the weeks following the Challenger disaster, the United States government established a special commission to investigate the causes of the accident, to identify the failures that had led to it, and to recommend measures to prevent such a tragedy from happening again. This body became known as the Rogers Commission, named after its chairman William P. Rogers, a former Secretary of State and Attorney General. The commission was composed of a mix of experts, including senior officials, military leaders, astronauts, engineers, and scientists. Among them, Neil Armstrong, the first man to walk on the moon, Sally Ride, the first American woman in space, and Nobel Prize-winning physicist Richard Feynman. The inclusion of such figures ensured that the commission carried both technical credibility and public trust, as the entire nation demanded answers in the wake of the loss. The Rogers Commission began its work by gathering testimony from NASA officials, engineers, managers, and contractors. Public hearings were held, broadcast on television, allowing citizens to witness the process of investigation and to hear directly from those involved in the shuttle program. One of the key tasks was to review the physical evidence recovered from the ocean, including sections of the solid rocket boosters, which revealed the erosion and burn-through of the O-ring seals. Engineers presented detailed analyses of how the unusually cold temperatures on the morning of January 28th had compromised the seals, preventing them from functioning as intended. The Commission quickly determined that the technical cause of the disaster was the failure of the O-ring in the right booster joint, which allowed hot gases to escape and damage the external fuel tank. However, the investigation went further, examining not only the physical failure, but also the organizational and managerial factors that allowed the launch to proceed, despite clear warnings. Testimony revealed that engineers at Morton Thiokol had expressed strong objections to launching in such cold conditions, providing data that showed the danger, but their warnings were overruled by company management after pressure from NASA to keep the mission on schedule. This discovery highlighted a culture where schedule and political pressure sometimes took precedence over safety, a finding that shocked the public and drew sharp criticism from the Commission. One of the most memorable moments of the investigation came from Richard Feynman, who conducted a simple yet powerful demonstration during a televised hearing. Using a glass of ice water and a sample of O-ring material, he showed how the rubber lost flexibility when chilled, dramatizing for the public exactly why the seals had failed on that cold morning. His blunt conclusion that, for a successful technology, reality must take precedence over public relations, for nature cannot be fooled, captured the essence of the Commission's findings and became one of the most quoted remarks from the entire process. The Rogers Commission's final report, released in June 1986, was a detailed and comprehensive account of both the technical and organizational failures that led to Challenger's destruction. It confirmed that the O-ring failure was the direct cause, but it also identified a flawed decision-making process within NASA, where management had normalized deviance by accepting previous O-ring erosion as an acceptable risk, rather than treating it as a serious warning. The report criticized the communication channels within NASA, pointing out that concerns raised by engineers were often diluted or ignored as they moved up the hierarchy. The Commission concluded that NASA's safety culture had eroded under the pressure to meet ambitious launch schedules and maintain political and public support for the shuttle program. In addition to its findings, the Rogers Commission made a series of recommendations for reform. These included redesigning the solid rocket boosters to eliminate the vulnerability of the O-rings, strengthening the role of safety oversight within NASA, improving communication between engineers and managers, and ensuring that the voices of technical experts could not be overruled by schedule-driven pressures. The Commission also recommended broader organizational changes to restore confidence in the shuttle program. The Rogers Commission and its investigation marked a turning point in the history of NASA. It exposed not only the technical flaw that destroyed Challenger, but also the human and institutional flaws that allowed the tragedy to occur. Its work demonstrated the importance of transparency, accountability, and respect for engineering judgment in high-risk programs. The investigation was not just about explaining the past, but about shaping the future, making sure that the lessons of Challenger would influence every mission that followed. The Challenger disaster was ultimately the result of a combination of technical flaws and organizational failures, and the Rogers Commission devoted much of its report to explaining how these two aspects were inseparable. On the technical side, the Commission confirmed that the immediate cause of the accident was the failure of the primary and secondary O-rings in the right solid rocket booster joint. The cold weather on the morning of the launch reduced the flexibility of the rubber material, preventing the seals from properly seating and allowing hot combustion gases to escape. This blow-by burned through the joint and produced the jet of flame that struck the external fuel tank, leading to structural failure and the destruction of the orbiter. Tests and recovered hardware demonstrated clear evidence of erosion and damage, proving that the O-rings were simply not capable of performing reliably under the conditions of that day. However, the Commission emphasized that the technical flaw was not an isolated defect, but a symptom of deeper systemic problems within NASA and its contractors. The design of the segmented boosters, chosen for manufacturing and transportation reasons, created joints that were inherently vulnerable to rotation and leakage. Engineers at Morton Thiokol had observed signs of O-ring erosion on earlier missions, and reports had been circulated describing the risks. Yet no decisive redesign was undertaken before the disaster. Instead, repeated incidents of erosion were classified as acceptable anomalies, and this normalization of deviance created the illusion that the system was safe, when in fact it was operating on the edge of failure. Organizationally, the Commission found that NASA's internal culture prioritized schedule and image over caution and safety. The shuttle had been promoted as a routine vehicle, capable of frequent flights that would lower costs and make space more accessible. Meeting these ambitious schedules required managers to downplay concerns and push forward despite technical warnings. The Commission uncovered evidence that engineers had urged delays when temperatures were too cold, but their voices were effectively silenced as decisions moved up the chain of command. Communication channels failed, and what began as strong objections from technical staff were watered down or ignored by managers under pressure to avoid delays. This structural weakness in decision-making was as dangerous as the technical flaw itself. The Commission also criticized NASA's fragmented safety oversight, noting that the Safety Office did not have sufficient authority to halt a launch, even when serious risks were identified. Instead of acting as an independent check on engineering and management, the safety function had been reduced to a formality. In practice, this meant that critical information about O-ring vulnerabilities never reached the top decision-makers in its full, urgent form. The organizational culture encouraged optimism and the appearance of progress, rather than a sober acknowledgement of risk. Technical warnings became bureaucratic paperwork rather than decisive reasons to stop a launch. The Rogers Commission concluded that these organizational failures were fundamental to the disaster, and that even if the O-ring had not failed on January 28, 1986, another aspect of the system could have caused catastrophe sooner or later, if the culture remained unchanged. Challenger's loss was therefore not simply a matter of bad luck or unfortunate weather, but the predictable outcome of a flawed process. The technical findings and organizational failures were deeply intertwined. The O-ring problem had been identified, but the organization failed to act. The data were available, but the communication broke down. The engineers spoke, but the managers did not listen. This combination of ignored evidence, flawed design, and cultural pressure created the conditions for tragedy. The legacy of these findings reshaped NASA, reminding the agency and the public that the most advanced technology cannot overcome poor communication and weak safety culture. Challenger became a case study in engineering ethics, illustrating that disasters are rarely caused by one technical defect alone, but by the interaction of design flaws and human decisions. The technical findings revealed the physical reason for the accident, while the organizational findings revealed the human reason, and together they explained why Challenger was lost. The Challenger disaster became one of the most important turning points in the history of NASA. because it forced the agency to confront not only a catastrophic technical failure, but also a deep cultural and organizational breakdown. The lessons learned from this tragedy reshaped how NASA approached engineering, safety, and decision-making, and these changes influenced every mission that followed. One of the most immediate lessons was the need to redesign the solid rocket boosters. The O-ring seals that had failed on Challenger were recognized as fundamentally inadequate, and a new joint design was developed with a third O-ring, improved insulation, and structural changes that minimized joint rotation. This redesign was tested extensively in a variety of conditions, including low temperatures, to ensure that the seals would maintain integrity under any foreseeable circumstance. The recovery and analysis of booster debris provided direct evidence for engineers to validate the changes, and the result was a much more reliable system that would serve the shuttle program for the remainder of its life. Beyond the technical fixes, however, the most significant lessons involved NASA's internal culture and management practices. The Rogers Commission had revealed that the decision-making process leading up to Challenger's launch was flawed because managers ignored or overruled the warnings of engineers. To address this, NASA made structural changes to its safety and communication systems. A new Office of Safety, Reliability, and Quality Assurance was created with the authority to halt a launch if risks were identified, ensuring that safety considerations could no longer be easily subordinated to schedule pressure. NASA also worked to improve communication between levels of the organization, encouraging engineers to raise concerns directly and creating formal channels for dissenting opinions to be heard at the highest levels. The disaster also taught NASA the importance of independent oversight. The Commission had pointed out that safety reviews within NASA were too closely tied to program management, leading to conflicts of interest. In response, new structures were implemented to ensure that safety evaluations were independent, rigorous, and not subject to the same pressures that influenced managers eager to launch. These reforms sought to restore trust in NASA's ability to balance ambition with responsibility. Another lesson was the recognition that spaceflight could never be routine. The shuttle had been promoted as a vehicle that would fly dozens of times per year, serving commercial, scientific, and military purposes in a way that resembled commercial aviation. Challenger proved that this vision was unrealistic. NASA scaled back its ambitions, reducing the number of missions per year and focusing instead on safety, careful planning, and mission-specific goals. The idea that shuttle flights could become routine was abandoned, replaced by a more sober understanding that each launch carried inherent risks that demanded constant vigilance. The Challenger disaster also emphasized the ethical responsibility of engineers and managers. In the years following the tragedy, the story of engineers like Roger Boisjoli, who had warned against the launch but whose warnings were ignored, became central to discussions in engineering schools and professional organizations. Challenger became a case study in ethics, teaching future engineers the importance of speaking up, documenting concerns, and insisting on safety, even when organizational pressures push in another direction. The broader public also absorbed lessons from Challenger. The presence of Krista McAuliffe, the teacher in space, had made the mission especially visible to schoolchildren, and the disaster left a lasting impression on a generation. For NASA, this meant that its public image could no longer rely on optimism alone. It had to demonstrate accountability, transparency, and a willingness to learn from mistakes. The years following Challenger were marked by intense reflection and reform, and when shuttle flights resumed in 1988, with the launch of Discovery on STS-26, NASA emphasized its renewed commitment to safety. The changes implemented after Challenger did not eliminate all risk, but they showed that NASA had absorbed the lessons of the disaster and was determined not to repeat the same mistakes. Ultimately, the tragedy taught NASA and the world that advanced technology cannot succeed without a culture that respects safety, listens to engineers, and places human life above schedules or political pressure. The lessons learned from Challenger reshaped the shuttle program and influenced the way space exploration is approached to this day, reminding everyone that in the pursuit of progress, caution and humility are as essential as ambition. The legacy of the Challenger disaster extends far beyond the technical details of the accident itself, because it reshaped the way space exploration is perceived, managed, and remembered, both within NASA and across the wider world. Challenger's destruction on January 28, 1986, became a defining moment in modern history, not only because of the lives lost, but also because of the lessons it forced institutions and societies to confront. For NASA, the disaster underscored the fact that spaceflight can never be routine. The shuttle program had been sold to Congress and the public as a system that would launch dozens of times per year, turning access to space into something reliable and almost commonplace. Challenger shattered that illusion, reminding the world that space remains an unforgiving frontier where small errors can lead to catastrophic consequences. In the years following the disaster, NASA scaled back its ambitions and adopted a more cautious approach to shuttle flights, with safety reforms, redesigns, and stricter decision-making processes becoming central to the program. The legacy also lives on in the way engineering and management are taught. Challenger became one of the most famous case studies in engineering ethics, appearing in textbooks, classrooms, and professional training around the globe. The story of the ignored warnings from engineers, the flawed O-ring design, and the pressures of organizational culture is now used to teach future engineers and managers about the importance of safety, communication, and ethical responsibility. The phrase normalization of deviance, coined in relation to NASA's acceptance of O-ring erosion as routine, entered the vocabulary of risk management, reminding all industries that repeated tolerance of anomalies can lead to disaster. In this way, Challenger's legacy has influenced fields far beyond aerospace, from medicine to civil engineering, wherever human lives depend on complex systems. For the astronauts themselves, the legacy is one of honor and remembrance. Schools, scholarships, and educational programs were named after Krista McAuliffe and her crewmates, ensuring that their dedication to exploration and learning continues to inspire future generations. McAuliffe's presence on Challenger symbolized the hope of bringing space into the classroom, and although her lessons were never delivered from orbit, her role inspired countless students to pursue science, engineering, and teaching. Memorials across the United States commemorate the crew, and their story is retold each year on the anniversary of the disaster, keeping their memory alive. Challenger's legacy also had political and institutional dimensions. The investigation and reforms that followed revealed the importance of transparency and accountability in publicly funded programs. NASA learned that it could not prioritize image over safety, and government oversight became more rigorous. The disaster also influenced how space policy was debated in Congress, with greater scrutiny placed on costs, risks, and the true capabilities of technology. Internationally, the Challenger accident served as a sobering reminder to other spacefaring nations that advanced programs carry immense dangers, and it reinforced the need for careful design and rigorous testing. For the public, the Challenger disaster remains a symbol of both tragedy and resilience. The images of the shuttle breaking apart in the sky, with trails of smoke marking the path of destruction, became etched in collective memory, but so too did the determination to continue exploring space despite the risks. When shuttle flights resumed in 1988, many saw it as a testament to human perseverance, a refusal to let tragedy end the pursuit of discovery. Challenger's legacy thus embodies both caution and courage. Caution in respecting the dangers of space and courage in continuing to explore it. The lessons of Challenger were tragically reinforced 17 years later with the loss of Columbia in 2003, another shuttle destroyed due to overlooked warnings and organizational complacency. Together, Challenger and Columbia stand as twin reminders of the price of neglecting safety and the importance of constant vigilance. Yet Challenger's legacy is not solely one of failure. It is also a story of progress, because the reforms that followed made the shuttle program safer, and the memory of the crew continues to inspire. Challenger showed that exploration always carries risk, but it also demonstrated the human determination to learn, to improve, and to honor those lost by striving to do better. The legacy of Challenger in space exploration is therefore one of enduring influence, a warning against complacency, a lesson in ethics and responsibility, a call to prioritize human life above ambition, and an inspiration to continue reaching for the stars with humility as well as hope.